Hello everyone, welcome back to Machine Learning Made Simple. My name is Christopher, and today we're going to be talking about hierarchical clustering. So sit down, hold on to your hats, because this is a pretty exciting one. Let's jump on into it. So let's first talk, as usual, the algorithm breakdown. This is an unsupervised clustering algorithm. There is no subcategory to this one. It has a complexity of O to the O of n cubed. And in order to make the most out of today's episode, it's recommended that you have a basic understanding of matrices and vectors. Just a basic understanding because we don't get too much. We use them, but we don't need to know a whole lot about them to understand the algorithm. So let's get started. So how does this algorithm actually work? So first, from a set of vectors, group the mutually closest vectors together. Repeat this process until our desired exit condition is met. So we're not going to be talking about vectorizing your data today, because we talked about that in our nearest neighbors episode in episode 1. So I'm not going to spend too much time talking about how to vectorize data and things like that. If you want to learn that, just check out that video. So what are some common exit conditions? Well, exit conditions, first of all, are reasons to stop iteration or iteration cycles. So, and again, more on this later. This is just a basic overview. We'll get into the nitty-gritties in a minute. So some common exit conditions we might want to use are a desired number of clusters have been created, because what we're going to be doing is we're going to be taking data sets. So say we have these data here, and here, and we have some data over here, and over here. With the power of machine learning, what we're going to be doing is we're going to say, okay, this is one cluster, this is one other cluster, and this is another cluster. And that's it. And these look like chocolate chip cookies. Actually, it's making me hungry. But yeah, essentially, once it's done creating its clusters, that's the algorithm. It's all done. We don't add any more data to it. What we can do, we can use this in a classification algorithm. So k-nearest neighbors, for example. So we can say, okay, we introduce a new data point here. Okay, it's k-nearest neighbors. It ends up in this cluster here. Now, the important thing to note about this this process here is that we never include this data point inside the cluster. We never change our clusters, because then we have the machine learning algorithm learning from itself, which can be quite disastrous in some cases. There are some algorithms which actually rely on this, which rely on the algorithm learning from itself, but this is definitely not one of them. And the reasoning for this, and I'll show you why in a second, because if we have a data point here, okay, it belongs to this cluster. If we have another data point here, okay, yeah, it becomes part of this cluster. Now if we have another data point here, suddenly our cluster becomes like this. And before you know it, we're saying things like a data point that's all the way over here belongs to this cluster, just because over time we introduced data points to it, which got further and further away. And of course, that's no good, because this, by looking at it, this looks like it should be part of this cluster right here. So that's why we never learn from its, have an algorithm learn for itself in this case. Again, there are algorithms which need to, but that's not this one by any means. So a cluster contains a desired number of elements. So basically, every data point is its own cluster at the very beginning. So we have 3 data points, we have 3 clusters. So if we say a cluster contains a desired number of elements, well, these two can form one cluster. There's 2 elements in this cluster, so that's done. So our clusters consist of this one and this one. But desired number of iterations have passed. More on this in a minute when we get into the math side of things. And these aren't all the exit conditions you'll ever need. It's all on a case-by-case basis. This is why data scientists get paid the big bucks, because anybody can put data into a library, import a library, and put in the data. But the reason data scientists get paid so much is because they're able to tweak and adjust the algorithm based on these properties, figure out what's the best exit condition to use in this instance, what's the best value of k to use in the k nearest neighbors algorithm, what's the best dimensionality to use in our polynomial regression algorithm. It's not actually algorithms that make up data science, it's actually using the algorithms and tweaking the algorithms to best suit the data. So essentially what we're doing is matching the algorithm to the data to get the most accurate results. So moving on, let's get into the fun stuff. So the first step, once we have all of our vectors, all of our data points in our grid, we have to create what's called a distance matrix. So we have to create a distance matrix between each vector. And then what we do is we cluster the mutually closest vectors together. We'll be talking more about this in a second. And then finally, the centroid of each cluster becomes the vector to use in the next iteration and the next distance matrix. And this repeats until we meet our exit condition. Mutually closest, again, we'll talk about in a second when we get into an example. Woo! Bet you didn't see that one coming. So say we have these data points here, A, B, C, D, and E, right? Well, first we're going to start off by creating a distance matrix. So how do we do that? Well, first we're going to need to pick an equation to use for our distance calculations. If you remember this slide from our k nearest neighbors episode, these are some of the distance equations we can use. In this episode, I like to use squared Euclidean distance, just because it encases all the numbers, unlike maximum distance. And we don't have to worry about the redundancy of this, the radical. It's not really redundancy, but if we're applying a radical to the result of everything, and that just takes up extra computational power, which we don't necessarily need, and then it turns everything into just a gigantic float, a decimal, instead of keeping everything nice, clean integers. So that's why I like to use squared Euclidean distance, but for the sake of today's episode and just simplicity, what we're going to do is we're going to go ahead and use the Euclidean distance. And if this all looks like alien to you, Euclidean distance is, if C is the square root of A squared plus B squared. This is, of course, when our dimensionality, or the number of items in our vector, each vector is 2. So if we have vector x, no, actually, if we have vector A, B, right, you can see there's 2 items in this vector, so A squared plus B squared. This is actually a really bad example. So let's say 1, 2, and then our second vector is 3, 4. This is going to give us 1 minus 3 squared plus 2 minus 4 squared. Oops, square should be outside these brackets. So 1 minus 3 gives us negative 2 squared plus 2 minus 4 also gives us negative 2 squared, which ends up just being 2 squared is 4, so 4 plus 4 is 8, and the square root of 8 is, of course, it's not a very nice number. It's a number between 2 and 3, so we can round up to 3. So it's about 3. So the distance between these two vectors would be 3. That's obviously how you calculate distance. In case I went off a bit of a tangent there. Sorry about that. So yeah, let's jump on into iteration 1. So here's our distance matrix. So here's the actual matrix form itself. I've created a nice little table right here. Here's a nice table, just so we can add these labels to it, which just makes it visually easier to comprehend what's going on. So from A to A, I put a dash because they're the same vector. So this is 0, but I put a dash because they're the same. But the distance from A to B is 5. Distance from A to C is 9.2. Distance from A to D is 9.5, and A to E is 13. Now, B to A and A to B are the same distance, right? It doesn't change which direction you go when calculating distances. So this matrix is guaranteed to be symmetric. This is going to be a symmetric matrix, which basically means we really only need to calculate these values here, but we put the rest in just to make it look all pretty and things like that. So the next question is, now we need to worry about the mutually closest vectors to each other. So we have vector A, B, C, D, and E, which are the mutually closest. So to figure this out, quickly erase all that ink just because it looked like it was crossed out. So say which vector is closest to A, is nearest to A. That's not A, because obviously every vector is closest to itself because of the 0 here. So that's one thing to note. If every vector you say is closest to yourself, you'll never get anywhere. In your iterations, you'll have infinite iterations and you'll never get anywhere. You'll never hit any exit conditions unless, of course, your exit condition is the maximum number of iterations. So we can see that the lowest number in this row here is 5. So the closest vector to A is B. Let's do the same now with B. The closest vector to B, the smallest number here, is 4.5, which is C. So A matches B, B goes to C. Let's look at C. The lowest number here is 4.5, so C also matches with B. Now let's go into D. D's least number is E, so D matches with E. And we go into E, E matches with D. Now, one thing to note is that in the event of a tie, so you can see that D, if it wasn't for E, our vector D would match closest with B and C, so in this case you just pick a random one of the two. And there we go, we've completed this little arrow thing. So next we have to say which ones are the mutually closest. So what this means is which vector had, okay, the vector it's closest to, is it the same vector? That doesn't make any sense. Let's do an example. It'll be easier to explain this way. So A binds to B. A is closest to B. So if B is closest to A, then these two are the mutually close. But it's not the case. B binds to C. So let's check C. Is C B? C, yes. Yes, C is closest to B. Therefore, they are mutually close. Let's move on. Now, once a vector has been used up, it obviously can't have any more mutual, you can't be mutually close to anybody else, so we can just skip over looking at C because we get the same result. So D is closest to E, and E is closest to D, so they also are mutually close. So what happens is we can create a cluster that is A, BC, and DE. So now we have 3 clusters. So the next question is, how do we calculate the centroid of BC and DE? Well, When I was first researching the algorithm, it wasn't very clear how you did it. So I thought, okay, we'll just treat each of these like a polygon, a closed polygon with non-intersecting lines. And that's how we can calculate the centroid, which of course uses this set of equations here, the set of formulas here. Yeah, that's not very fun to calculate. So there's an easier way of doing it, which is just simply take the average of all the x values, and that's going to be the x value of our centroid, and the y values is going to be the y value of our centroid. So let's put this into practice here. So we have this table here. These are the same numbers we started with before. So the centroid of BC, you can see we take the average of the x because B's x values, so this is BX, and this is CX, CX, this is BY, and CY. And then we take the average and we end up with 1110, and that is the centroid of BC. Next is DE, so we do the same. This is DX, this is EX, this is DY, EY, and we end up with 1610. So when we graph this out, we end up with something like this. We update our graph. You can see now we have 3 clusters. And I've X'd out these ones because we no longer need those. From now on, when we're calculating the distance, for our distance matrix, it's not A to B, A to C, it's now A to BC, A to DE, and DE to BC. So that's how that's going to work. The other thing to note is when we calculate the centroids, we don't use BC and DE. So say A happens to, in this next iteration, A is closest to BC, then we'll take the average of A, B, and C, and that'll become ABC. So let's move on to the next iteration. We calculate our distance matrix. Again, here's our actual matrix itself, and here's our symmetric matrix and our little table here. As you remember from our last iteration, we are now with this cluster here. So let's take a look. So the closest vector to A is BC, which is a distance of 7. BC is closest to DE, so BC is closest to DE, which is 5, and DE is closest to BC. Now you see how A got left out? There's no A on this side, and that happens. So let's look at the mutual closeness. A to BC. Does BC go to A? It does not. BC goes to DE, and DE goes to BC. So these two are mutually close. We combine them together, and we now have our newest clustering, which is A, and then BCDE. So again, calculating the centroid of BCDE is simply taking the average of them. So this is BX, CX, DX, and EX, and BY, CY, DY, and EY. And this gives us a centroid of 13.5 and 10. So when we graph this out, you can see that this becomes one cluster, and this becomes another cluster. We now have 2 clusters. Okay, so let's now move on to iteration 3. And if you remember, this is where we left off here. So A is closest to BCDE. BCDE is closest to A, as you remember from last time. Are they mutually close? Well, A goes to BCDE, BCDE goes to A. They are, in fact, mutually close to each other. And so our final clustering looks like this, A, B, C, D, E. And then we go with this table here. We calculate the centroid. So this is A, X, B, X, C, X, and so on. This is A, Y, B, Y, C, Y, and all the way on. You get the picture. And this ends up with a centroid of 12, 9. So we graph this out, A, B, C, D, E, and this is all one cluster. All one cluster. Hang on a second. That's not very useful. If this algorithm just clusters everything into one cluster, then what's the point of using it? And that's because we forgot one very important step, and that is, in fact, the exit condition. This is important because if you let this algorithm run for enough cycles, eventually it will cluster everything into one giant cluster. And we don't want that. That's not very useful, is it? So we have to come up with an exit condition. And from the exit conditions we talked about before, let's just go through some examples just to show you what different exit condition results would look like. So if we were to go through 3 iterations, 1, 2, 3. So this is iteration 1, iteration 2, iteration 3. So we'd end up with A, B, C, D, E. If we went with 1 iteration, then we'd end up with A, B, C, D, E, this one right here. So what happens if we say go until a cluster has exactly 2 items? So this is cluster 1, 1 item, 1 item, 1 item, 1 item, 1 item. So there's no clusters with 2 items. So we move into iteration 2, 1 item, 2 items. Stop, and we can complete the iteration. At the end of the iteration, this is what we'll do this check. A, B, C, D, E, done. The next one gets a little bit more complicated, which is go until there are exactly 4 clusters. So in step 1, we have 5 clusters. In our first iteration, we have 3 clusters. Our second iteration, yeah, sorry, brain fart, 2 clusters. And our final iteration, we have 1 cluster. So we'll stop when we have 4 clusters. So, there's no cycle when we have exactly 4 clusters. So you can get around this by saying when the clusters are less than or equal to 4. So in this case, 3 is less than or equal to 4, so this is when we would stop. That's one way of coming around this. Or if we need exactly 4 clusters, because we'd end up with 3, then what we would do is we would stop the moment 4 clusters become a thing. So the question we have to ask is, going back to this table, and we will only cluster the ones that are closest. So what's closer, B to C or D to E? So if we look at this table, B to C is 4.5, 4.5, and E to D is 4.5 as well. So the distance between both are both 4.5. So this is a problem because neither of them are closer because they're equidistant. So in this case, and really the rule of thumb when it comes to machine learning algorithms, in the event of a tie, random. Pick a random value. This is the easiest way to prevent any programmatic bias, which obviously we want to avoid as much as possible when writing these algorithms. So the result of this, if we were to say go till if there's 4 clusters, would be either A, B, C, D, and E, or A, B, C, D, and E. Either of these could be the correct answer. And in both cases, we have exactly 4 clusters, which ends up being our result. So anyway, thank you for watching this video. If you have any questions, please leave them in the comments, and I'd be happy to answer any questions you may have. You can like and subscribe if you want. It's really up to you. Much appreciated, though. Thank you for taking the time to watch this video, and have a nice day.